All right, so let's just continue this wave terminology a little bit further. We looked at the longitudinal waves and transverse waves and orbital waves. So longitudinal waves are also called push-pull waves. Think of pushing a spring or pulling a spring and letting go. It's going to vibrate longitudinally, like somebody is pulling it and pushing it, or they compress and decompress as they travel, right? So you can imagine, as I'm talking, air is being pushed and pulled, and the pressure wave travels, and your ear is interpreting it as a sound wave, right? So just to make a poor joke for you, Saurabh, if a tree falls in the forest, will it make a noise? No, it will create a pressure wave, and if you are there to hear, then it's your ear that converts the pressure wave into sound. Okay, big deal. All right, so the transverse waves are, as I said, you tie a rope, you pull it up and down on one end, and you get this waveform that's going side to side. Unlike the compression waves or the push-pull waves and longitudinal waves, same thing, the energy is traveling in the same direction as the wave form. Whereas if you imagine the rope is moving up and down, and the form is moving forward. So the energy is actually traveling at right angles to the direction of moving particles. Okay, that's something to remember. These waves are generally only transmitted through solids, not liquids. So rope is a solid, or a table that for the compression wave is a solid, right? These are also called body waves because they only travel through solids. Orbital waves, called interface waves, because we said it's traveling between the air and water. So waves on the ocean surface are the orbital waves. The terminology is there for these kind of waves. You have a crest wave, where the molecules or water parcels rise and then they begin to fall. There's a trough at which they hit the bottom and then they begin to come back up. Is the wave form. We will see an animation later on. So there are crests and there are troughs. And in an idealized situation where you have no winds and the water is just still, you actually have a still water level. But you can imagine in the real ocean there is always wind and there are always ripples, or the ocean is moving because of the currents, and then the waves are riding on top, right? Nonetheless, for definition's sake, in a still water level, the distance from the water level to the crest or the trough, because it is idealized, it's a perfect circle. We will see that that's not also the case always. You have the wave height, and the wave length is a distance obviously from a crest to a crest or a trough to a trough, because idealized wave has perfect sinusoidal forms. How do you think about it? Let's say you're sitting at a pontoon, or I don't know, whatever, the jetty on a water, and you see the waves moving by, and you have some kind of a reference, let's say a pole, and you can see crests coming by and troughs coming by, and you can kind of try to measure the distance between two crests or two troughs, and that'll give you a wavelength. But what you see here is that as you go deeper into the water, the waveform is going to die away, because the energy that is producing the waves is at the surface, and that energy can travel only so far down in a heavy medium like water, right? So at some point the wave impact disappears. That's called the wave base. So if you're a submarine, you're going to try to avoid this wave perturbation and go below that, but then you will have internal waves as we talked about. So this is the basic terminology of the transverse or longitudinal and transverse and orbital waves. Very simple stuff. I'm sure you have seen it somewhere, but it's better to just make sure we understood it once again. Okay? Let's continue after this.